Good morning, everyone. For this session, I'm going to present a research study conducted in Hong Kong about the mobile air sensor network. The content is mainly published already in the environmental pollution last year. I myself is Professor Ning. I'm from the Hong Kong University of Science and Technology. Now, before I move into the details about the study, I want to give a little bit quick review about where we are and why we want to conduct the study. If you look at this publication, the numbers in the literature over the last 10-15 years, we see a very sharp rising trend of this publication around the sensors. If we use a keyword air sensors and air quality monitoring, we can also see the major work is still around the sensor development and also the environmental science, which is relevant to the applications. So that means the conference like this one about air sensors, we see a quite important in the future. So that's also why we put a lot of effort in the research on this. But the more we look at the data, the more we look at the applications of the sensors, we also see there's limitations and also there is good hopes. For example, where we are now about the sensors can or cannot, from our understanding, when we look at the different target pollutants, for sure there are different working principles of the sensors. And based on these different principles, there are different major issues. For the gas and the PM sensors, which is the major sensors we used in the study, they still suffer quite a lot of issues. For example, the PM sensors, even though they have been well developed, but we still know the humidity impact, the refractive index variation for different kinds of pollutants can have impact. And for the sensors, which is actually quite critical for understanding the urban air quality, it is the we can still see a lot of inconsistent performance in the literature. So in this study, what we have done a little bit different, which is the we work around the air quality sensors and try to find the best physical solution and for sure the mathematical solution. And when we look at the sensors data, the two key issues we identify is one is a humidity shock, in which when you have transient IH changes, you can see the sudden change of the voltage and output from the sensor signal. So that for sure, that's something we need to solve. The other problem is the temperature fever. In a way, it's just really like our human. When we see the temperature going up about 35 degrees C, if you put 100 sensors in one batch and go through a different temperature and a humidity cycle, you will see individual sensors, they have a huge different responses in terms of the temperature impact. So that's something we have to pay attention, we have to keep in mind when we look at how to solve these air quality sensor issues. So in the work we have done, we have used this dynamic baseline tracking, in which we have this continuous monitoring of the blue line, which is the dynamic baseline. So in this way, we can do something quite interesting, where we can chase after some level of the traceability of the air quality sensor data, especially for the gas sensors. So for example, what we have done in the past quite a few years is to validate and demonstrate if the sensors can achieve the level that we can trust, regardless of these ambient conditions. Here, what you can see, the yellow shadow is where we do the laboratory calibration with multiple point. Typically, it's quite typical thing we do even for the reference analyzers. Then we move on to the field, and in comparison to the reference analyzers, and between the laboratory and the field validation, these two references or standard gases, they share the same traceability. And then we go through the cycle again. We do the field calibration using these standard gases in the field when the sensor is in operation. Then we leave the sensors running for another long time and try to see the comparison. So here we can see, regardless of the temperature and humidity changes in ambient conditions, they can vary from 20 to 35 degrees C. Temperature-wise, they can even go from 40 to 90% humidity. We can still see the traceability and still maintain pretty well. Now, this study, we don't have time to present in details in the study, in this presentation, but just to give a sense of how the effort of air quality, the validation and the quality control can be important. Now, moving on, when we look at this, the air quality sensor applications, there are different things that have tried in the past. So today, I just present one interesting result about the mobile sensor network. For others, we have done different studies, and welcome to check out the literature and also our conference presentations. So now for the mobile air quality sensors, we have done 2 major studies, some other smaller ones, but the major studies also accidentally represent 2 very different applications. Number one that you can see is a random route by taxi. This one was done in the Shanghai and is still going on, lasting for almost 2 years. So this one is a mobile sensor, but it's a fixed route based on the buses. So these 2 studies has very important characteristics. For example, in Shanghai, when we look at this one, we have over 150 taxi. They go by random route and random time. And we have, after 1 month's time, you can cover quite a large portion of the entire roadway network. You can generate a huge amount of the data as well. But for the fixed route, we have selected 14 bus routes, and it's the same route, same time every day, and we accumulated over 6,000 bus trips. And you can see you can still cover quite a lot of roadway network. But the difference between the 2 is, even though for both cases, the time and the space dimension, they change simultaneously. But this one, the coverage of this roadway network by the taxi versus the coverage of the fixed route, they are not the same characteristics. So how we can deal with this kind of a different nature of the sensor network is in terms of the random route, for example, when we run it by the taxi for over some time period, the roadway coverage can go from, if you have 150 taxi, for example, it can go from 0 day, 1 day, and up to 30 days. You can see how many percentage of the coverage. In other words, how many taxis or how many days would be enough to cover your city's network, roadway network. The same thing you can also see once we have this, the roadway coverage here, and how many taxi in 1 month's time. How many taxis will be needed in order to achieve certain coverage percentage. So in Shanghai, this is something we have done. Now in Hong Kong, when we look at the fixed route, it's also interesting because when we put these 14, the different routes all together, you will see this is a grand average of these 14 different routes, bus routes. So you can see actually they have very consistent the speed profile, the locations and the coverage of different areas, day by day and trip by trip. So in this way, when we have these sensors carried by the buses, they go from A to B and B to A and back and forth. We have a chance to see the repeated pattern of the air pollution distribution along the same route. At the same time, the variation during the day by different hours will also give us a chance to look at how this air pollution can change in the on-road conditions. Now that's one important thing about the fixed route air quality mobile sensor network design. The second thing is also about the separation of the background and local signal, because when we put up few high resolution, 5 seconds, 1 data point all together, and you can see when we have a different routes of the buses, put them together in one single chart, you will see even though there's a black line which represents the local the instantaneous air pollution concentrations. But the bottom here, the red line here, these seem to be shared among different routes during the same time period. So this gives us a chance to think what is the physical meaning or what is the science behind this important data. So we can see from here, when we look at the black line, which is important, the high frequency signal, but at the same time, the red one seems to be a low frequency signal. So when these two combine, this is what we see. But if we have a chance to see when we have a different routes, this red line has been shared by so many different routes. This one must mean something. So we have found different ways to do it. So we did the baseline extraction algorithms to compare the DWT, lower percentile measured, and the moving window, time window, etc. So you can basically see when we have these continuous measurements of the air quality data. So we try to identify automatically what is the baseline information here. So given by different the extraction methods, we identify the best approach. Then afterwards, we have a chance to see, okay, these are the different routes, these are the different pollutants. Over a certain time period, we can identify what is the percentage contribution of the background, which is a darker shadowed area, versus the local, which is a light color shadowed area. So you can see the separation between the baseline or the background versus local can also mean very different messages for different pollutants. So basically for PM, is mostly a regional pollutant, as we all know, and you can see a large portion of the background has contributed to the city air quality. At the same time, when you look at the NO and NO2, they are mostly local emission driven. So you can see 80% of this pollution, actually they are local. So this will be very useful information for air quality management people to see into details and see in different roadway sections, if we can identify a way to separate them, what is the effort we should make in order to control them more targetedly. A mobile sensor is not only about the on-road. At the same time, I just want to give a snapshot of what's going on in our research group. So we also have done different kinds of the sensors. This is the sensors on the drone. We have put onto the drone for the measurement of the ship emissions to identify the fuel sulfur content. We are working with the government at the moment now. We have renovated helicopters operated by government flying service departments. So we can carry the sensors and measure over a large area in a short time period. We also put the sensors on the Tesla balloon to go up to 1,200 meters in order to study the boundary, the planetary, the PBL. So this is a quite interesting things we do. And for the helicopter, you can see we renovated the helicopter. We have the sensors and the VOC canister sampling, so we can actually capture quite important information. So afterwards, you can see this is from the aircraft. At the same time, we have these ships carrying the sensors also. So you can see the mobile sensor application is not just limited by on-road or the land basis. When we go to the ocean, for especially the study of the ozone, you can see how the distribution of the pollution can be across these the different waters. So that's actually a very quick snapshot or shot of what we do. And the way forward we see is we hope the new technology development can bring new insight about air quality studies and of course the scientific air quality measurement. We also see many challenging environmental problems. They need to be more work in the future. Okay, we are also thank for different agencies to support the project. Thanks, and we welcome to any of the questions if you have any.